Hello everyone, welcome back to my YouTube channel. So today we are going to solve problem number 1948, delete duplicate folders in system. Let's read the problem statement. Due to a bug, there are many duplicate folders in a file system. You are given a 2D array paths where paths of I is an array representing an absolute path to the ith folder in the file system. Okay, so for example here if you see this array, okay, array of strings, so this is just one complete path. Okay, so it represents the path 1 2 3. Okay, so these are all the subfolders, okay, inside one another, right? So root, then 1, then 2, then 3, okay, like this. Okay, two folders not necessarily on the same level, okay, I'm talking about two folders, are identical if they contain the same non-empty set of the identical subfolders and underlying subfolder structure. Okay, so folders are going to be identical if they contain the same non-empty set of identical subfolders and underlying subfolder structure. Okay, the folders do not need to be at the root level to be identical. Okay, if two or more folders are identical, then we have to mark the folders as well as their subfolders. All right. Okay, so let's understand this with an example here. So it is saying that folders A and B in the file structure below are identical. They as well as their subfolders should all be marked. Okay, let's see how. All right, so let's say this is one root. Okay, from root it is starting. Okay, then after that we have A. All right, so here we have A, then here root A, then here like this, then X is there. All right. Okay, so this is root, then we have A. Okay, then here A, after A we have X. Okay, done. And here after A we have Z also. All right, clear, done. Now again here another folder, it is starting from the root only. Okay, so let's say this is my root. Okay, so here let's say B. All right, now here after B we have X. All right, done. Okay, then after X we have Y also. Okay, all right. Okay, here also after A we have X, then Y also we have, right? So here let's add this also. Okay, then after B we have Z. All right, so let's mark Z. Okay, this is done. Now here if you see, this is my root. Okay, this is my root, let's say. All right, and let's say this is my folders. Okay, folder A, and this is my folder B. Okay, now these are the subfolders, let's say. All right, so now here if you see one thing, for this X, this Y is the only children, right? So after X we have just Y. Okay, so can I just write Y here? Okay, let me use some other pencil. Okay, can I just serialize this X node as Y? Okay, it is just showing that after this X we have just Y. Okay, same way here after this X we have just Y. Okay, now here if you see one more thing, now if you see here we have A, right? So after A what we have? After A we have X, Y and Z. Okay, that's it, right? So here I can say after for this node A, I can serialize this node A as, okay, so below this A we have X, right? And for X we have this Y. Okay, and same way we for this A we have Z also. Okay, now if you see this B, okay, for this B we have one child X. Okay, and X has Y. Okay, so done. Then this B also has Z. Okay, now if you see here one thing, right? So this folder A and folder B are identical, right? Okay, for this A we have X, Y and Z. For this B we have X, Y and Z. Okay, so two folders A and B are identical if they contain the same non-empty set of identical subfolders and underlying subfolder structure. So see, structure is also same, right? X, Y, Z, X, Y and Z. Okay, all right, this is done. Okay, clear, right? Okay, so now here this is done, right? Now after that it is saying, however, if the file structure also included the path this root, then B, then W. Okay, root, B and then W. Okay, Now let's add W here. Okay, now if I add W, then the folders A and B are not would not be identical, right? So here after this W is also there. So now see, for this A, X, then X child B, Y, then Z. For this B, X, X child Y, then Z, and then W. So they are not identical. Okay, now it's issue, right? So now we can't delete this. Okay, but here in this case we can delete this part and this part. Why? Because if I treat this X as my folder, okay, X as my folder, and this X as my folder, okay, so now here see, X has just Y children, okay, and here also X has just Y. Okay, so I can delete this, right? Clear? I can read this, but I can't read A and B because they are not identical, because A has X, X tilde Y, Z. B has X, X tilde Y, Z, and W. Okay, this is done, right? So note that AX and BX would still be considered identical even with the added folder. Okay, so that's why we can delete this. All right, so once all the identical folders and their subfolders have been marked, the file system will delete all of them. Okay, the file system only runs this deletion once. Okay, so any folders that becomes identical after the initial deletion are not deleted. Okay, clear with this line? Very easy line, right? So we have to return the 2D array answer containing the paths of the remaining folders after deleting all the marked folders. Okay, the paths may be returned in any order. Okay, so I hope that you guys are clear with the problem statement. Okay, all right, so now here I am writing, if you see this particular example only, x child is y. So here I am writing y, and I am writing it like this. Okay, in this open and closed parenthesis, right? Why I'm writing like this? Okay, let's understand this. Okay, before proceeding further. Okay, so let's say you have this one node A, and here you have this node B. Okay, they are both are coming from some root. Okay, let's say this is my root. Okay, now this A has child C. Okay, then here D. Okay, and then E. All right, clear? Okay, same thing here. For this B we have this child C. Okay, we have this child E, let's say, and we have one child D. All right, so now here, if you don't write these open and close parentheses, what is going to happen? Okay, so this D, okay, so I can serialize this node C as serialize simply means I am writing the children here. Okay, for this node, for this is leaf now, so there are no children for this, so I'm just leaving it empty, null. For this C, D is the children. Okay, for done. Same way for this C, E is the children. All right, so you are going to say no need to delete. Okay, nice, no need to delete, right? Not matching. Okay, for this A, now see the complexity here. The childrens are D, C, E. Here also I can say D, C, E. Okay, let's say I have sorted them. I have sorted them. Okay, C, D, E, C, D, E. Okay, now there is one more question. Why I need to sort them? Why I need to sort them? So I will show you. Okay, why we need to sort them. All right, so let's say again, this is my root, this is one folder A, and this is one folder B. Here we have C, and here we have D. Here we have D, here we have C. All right, so now this A folder has two subfolders, C and D. Same way for this B, it also has same subfolders, na? DC, right? So that also means that they are identical only, right? Just order is changed now. In this B, folder is same, D and C. Okay, but just D is coming first and then C. Here for this A, folders are same. Okay, D and C, but just C is coming first, D. Okay, so that is why sorting is needed. Okay, so here I have to delete this. Okay, A and B definitely are identical, but I can, if I compare this CD and DC, they are not matching. Okay, so if they are identical, so what I'm going to do, the serialized key that I'm going to write here. Okay, how I'm going to do serialized, I will just sort them. Okay, CD, now they are identical. Okay, this CD is matching with this CD. Okay, now I can easily delete this. right? So that is why sorting is needed. Okay, so now here if I write it in sorted way, CDE, so I'm going to delete these two, but this is bad. Why this is bad? Because here D is the subfolder inside B, but here D is the subfolder inside C. Okay, E is subfolder directly inside A, but here E is a subfolder inside C. Okay, so that is why I am going to use open and close parenthesis. Okay, so now how it is going to help? Okay, so if you just don't use this open and close parenthesis, you are going to do the deletion here itself. Okay, and that is not right. Okay, because C subfolder is D here, and here C subfolder is E. Okay, so this is bad. All right, so that is why we need open close parenthesis. Okay, so what I'm going to do, D C a child is this D only, so I'm going to write it like this. And now here what I'm going to do, A first C and C's child is D. Okay, C and C's value. Okay, C and C's value is D. Okay, and then E. Same way here, B C and then C's child is E. Okay, C's child is E. All right, and then D. Okay, so now they are not same. Okay, these two strings are not same. I'm not going to delete them. Okay, so I hope that you guys are clear why we are doing the sorting and why we need to use open and close parentheses. Okay, done. Okay, this is done. Right, now after this let's understand the examples. Okay, so here, okay, first thing, paths are given to us like this. Okay, so here if you see, this is list. Okay, inside this we have more lists, like this. Okay, right, and inside this list we have what, we have strings. Okay, we have strings inside these lists. Okay, so this is how path is given to us, right? Okay, so now here we are always going to start from the root. Okay, so let's say this is my root. Okay, so this a means from root to A. Okay, right now A is not there, I'm going to add this A. Okay, so again C means start from root and then C is not here now, so I'm going to add C. Then here D means start from root and then D. Okay, so I'm going to add this D. Then here AB means start from root then A is already there, then B. Okay, C is already there, then B. Okay, let's add this. D is already there, then add A. Okay, let's add it. So this is nothing but my trie data structure. Okay, trie data structure. So I hope that you guys are already aware of this. If not, I'm going to cover the basics also in this video. Okay, the definition, what is this definition? Okay, how it is working, I will cover all this. Okay, I will just take 2-3 minutes for this. Okay, for this explanation. All right. Okay, first we need to create this trie. Okay, this is done. All right, so now here if you see B, A's child is B. Okay, so I can simply write here B. Okay, C's child is just B. Okay, I'm going to write like this. D child is just A. I'm going to write like this. Okay, now for this root here if you see, I have A and A child is B. I have C and C's child is B. Okay, I have D and D's child is A. All right, so now here if you see, if you notice one thing, this open bracket, okay, open parenthesis B and this close, and here open B and close. Okay, this parenthesis, this is appearing 2 times, this is just appearing 1 time, this is also appearing 1 time, so I am going to delete these two. Okay, I'm going to traverse from top again, and when as soon as I reach this node A, I see I will get this serialized string. Okay, and if the count of this, okay, so definitely I'm going to use one hash map also. Okay, in that hash map I will store the how many times this string appears. If it is appearing more than 1 times, I'm going to return from here. Okay, I'm going to traverse from top, I'm going to simply return from here. Okay, I'm not going to add this in my new path. Okay, so in that there is one D starting from root. Okay, so D, then there is one A starting from root, so we have D and A. Okay, so that's what we need to return. That's it. Clear? Okay, now see this example number 2. All right, so very good example. Okay, so we have A, then C, then starting from A, then B. Okay, then C, then B, then A B X. Okay, then A B X Y. Okay, then W. All right, then W Y. Okay, so now Y X, here I can say na Y. W, for W I can write it like this. Okay, for others you will not see the same serialized. Okay, for this B, how you are going to write, let me write now. So for this B, how you are going to write, so B's child is X, and what is X value? x value is inside this y. That's it. Okay, done. Right, now what is this a value? A's child is b. Okay, and what is b value? B value, this value. Okay, just put it inside this x. Okay, y. Done. Clear? Now this is done. Okay, now here this c value, just b is there. Okay, just b is the child. Right, done. Okay, so this is what we were doing right here, like this. Okay, child. All right. Okay, so now for this w, only y. Okay, this is done. Now in the top, what we are going to have? We are going to have a. Okay, a, one child, and inside this a, what is the value of this a? If you see this, this is what we need to put inside. Okay, b, and then b's child is x. Okay, and x is consisting of what? Y. Okay, just add this. Done. Okay, then we have c. C's child is b. Okay, add this. All right, and then we have, okay, then we have this w child is y. Okay, just add this. All right, clear? Okay, this is done. All right, so for this b, we have x, and x value is coming as y. All right, so we have to just go to this. Okay, that's it. Okay, so you will count the frequencies of all this. Okay, I will just go over these details also when I'm going to debug the code. Okay, same way for this example 3, b child is just a child is b only, c child is d only. Okay, not identical, so we are going to add everything. Okay, right, so these are very actually simple examples. Okay, only one path, right? This a, then b, then okay, non multipath. So for multipath, I have already covered this scenario. Okay, why we need to do the sorting. Okay, and why we are using open and close parentheses. Okay, when we have just complex structure like this. Okay, so this is done. Right, so now let's understand what is trie. Okay, so trie is nothing but a tree like data structure which is used for storing the collection of strings. Okay, especially when there is a need to perform the efficient lookups like prefix searches, okay, or insertions. It is also known as prefix tree or deletion tree. Okay, so here representation, how we represent trie node. So trie data structure consists of nodes connected by edges. Each node represents a character or a part of string. The root node acts as a starting point and doesn't store any character. Okay, right, and path from a root to a node represents a prefix. Okay, done. So now here, see this trie data structure a and d. I have to insert this word. So what I'm going to do, so root node, and then after that a is not there, so I'm going to add a. Then after that n is not there, I'm going to add n. Then d is not there, I'm going to add d. Okay, now next time when I'm going to insert aunt, again I'm going to start from root. A is already there, n is already there, t is not there, so I'm going to create a new node aunt. Okay, same way for other words we have to do. Okay, that is done. So this is the basic structure of trie node. Okay, in Java. So we have one class trie node. Okay, we are going to create one class trie node, and inside this we have children. Okay, let's say we have lowercase English letters, right, a to z. So that is why this children array. Okay, so a is 0 index, okay, b is 1 index, z is 25 index. Okay, so that is why. Okay, and is end of world, we are going to create one variable. Okay, so is end of world, just showing that here we have, there is one word which ends at this position. Okay, a and d, that's it. Okay, so initially I'm going to set it to false. Right, so what are the different operations? We have operations like insert a word, search a word, and prefix search. Okay, these are the operations, right? Okay, so now how we are going to do the insertion? So let's suppose I want to insert a word a and d. Okay, and right, so again I'm going to start from root always. Then I'm going to check first character. Okay, a. So what is the index of a? 0. Okay, so right now starting from here, node dot children 0. Okay, node dot children 0 at 0 index, so it is null. Okay, right now there is no a, right, node. So if node dot children index value is equal to null, then I'm going to create a new trie node at that particular position, right? And once I create this, then I'm going to reach here, right, and then I will start searching n. Okay, so after this a, n is not there, I'm going to create n. Then I will reach n. Then after that n, we don't have d, so I'm going to add the d. Okay, so once all this is done, once I insert the word, I'm just going to update this node is end of word. Okay, add this node end of word, I'm going to mark it to true. That simply means that here one word ends. Okay, we have completely inserted the word. Okay, so this is done. This is how we insert a word. Okay, now how we search a word. So let's say I have to search a and t only. So again I'm going to start from root always. in the tree. Okay, then I'm going to iterate over all the characters one by one, and I'm going to check the index. Okay, so if A is there, fine. Okay, let's proceed our search. But if A itself is not there after root node, then simply return false. Okay, all right, then after A, once you reach A, then go to A node, then search for N, then go search for this. Okay, so once you reach complete this word, okay, then just check what is the value of node is end. Okay, is end of word. Okay, so just return that value. Okay, you are going to return true. Then prefix search we are going to use. Okay, so let's suppose we are searching if we have this prefix an. So tree node root. Okay, again you are going to start. Okay, you are going to check if that index is there. If it is not there, simply return false. If it is there, go to this. Okay, then go to this. Okay, if you complete this and you still didn't execute this false, then just return true. That's simply that this prefix is there. Okay, so these are the operations. So time complexity, insert, ofl, search, ofl, prefix search, ofl. Okay, where L is the length of the word or prefix. Okay, so advantage, fast search and insert for strings. It is efficient for prefix based operations. All right, so this is done. Okay, so now here one more thing, if you notice here, when I was writing this C open bracket D close bracket E, okay, or this, so first uh, for the serialization of this node, I am checking the children's first. Okay, for this C, I am checking all the children, so only I have D, right? Okay, same way for this A, first I am checking the children's. Okay, all the children's here, and then I am going to process the node. So it's like how I'm going to do the traverse. So I'm going to start from top. Once I'm going to check the all the children's for one particular node, and then I'm going to do the serialization. So I can say that this is nothing but my post order type traversal, right? So I hope that you guys are aware about the traversals. Okay, if not, let me also explain. Okay, very quick. So we have three types of traversal. Okay, one is pre-order traversal, one is in-order traversal, one is post-order traversal. Okay, so how you're going to remember this? So it's very easy. Okay, so we have left. Okay, then we have mid. Okay, then we have right. Okay, so here mid here. Okay, mid here, just place mid here for the pre and then LR. Okay, for post LR and then place M. Okay, so this is very easy way to remember. Okay, so L is always going to come first, then only R will come. Okay, so in order means simple LMR. Okay, left mid right. For pre M place here, for post M place here. That's it. Okay, now I can prove this with an example of this binary tree. Okay, so first in order means left mid and right. Okay, so I start from here, left 2, then here left. Okay, so 4. Okay, then mid, then right. Okay, then 4 to 5, then right, left, mid and right. Okay, done. Now this complete is left. Okay, this is my right, and then this is my mid. Okay, so now after that 1 and then 3. That's it. Clear? Okay, this is in order traversal. All right, now here after that pre-order traversal. Pre-order means mid, left and right. Okay, so first this is your mid. Okay, this is your mid, and then this is your complete left, this is right. Okay, mid, left and right. So first you are going to write mid. Okay, one is done. Now you move here. Okay, after that we move to left now. So in this left, this is complete. Okay, for this complete, this is mid. Okay, you are going to write this mid, then the left, then right. Okay, and then this and right. Okay, that's it. This is pre-order. Done. Now same way, post order, simple. Left. Okay, so first left, then right. Okay, left, right, and then you are going to write mid. Okay, 2. Okay, then this complete is left, this is right, and then this is mid. Okay, then right 3 and then mid. Okay, that's it. Okay, so you are clear why we need to use the post order traversal. Okay, why we are using this. Okay, so we need to process the children first, then for the serialization. Okay, this is done. Now let me explain the example. Okay, debug statements. Okay, so how we are going to debug this. So first, simple, build a try tree. Okay, so you already know A, then C, then a D, then A, B. Okay, I'm going to build this tree. Okay, once this is done, then I'm going to start the serialization of try. Okay, so recursion into child A, then the recursion into child B. B, there is no children, I'm just going to skip it. For this A, I'm just going to return this B, and inside this nothing. Okay, null. Okay, done. All right, Same way C, B, there is nothing inside B, then for C I'm just going to return this B null. Same way recursion into child D, inside this A, okay, there is nothing, so I'm going to return this A null, okay, like this. So in the top you already know A and A for A we have B and null, okay. For this C we have what? We have B and null, okay. For this D we have D, and inside this what we have A and a null, okay, like this. So this is done. Now again we have to count the frequencies of all these side by side. So here this is occurring 2 times. Again I'm going to remove, we have to remove the duplicates, so we are going to again traverse from the top, okay. So traversing to child A, okay, duplicate found, right? So this frequency is 2, right, greater than 1. So I'm just going to do the backtrack, okay. Traversing child C, again duplicate found, right. I'm going to return back, okay, backtrack. Then we are going to traverse to child D, okay. So now we have to add this, okay. So we are going to add this D, okay. So how, here we are returning, okay. Once I reach this D, I see that we this is occurring just one time, okay. So I'm just going to create one path, okay. I'm going to add this, okay. And after this I'm going to process this, but before that I'm just going to add this into my result, okay, final result, okay. This path I'm going to add to final result, okay. Once this is done, I reach here, okay. So this path I'm going to update here. Initially it was D now, so now I'm going to add A here, and then I'm will going to add this also in my path, okay. First, until here there is nothing, okay. This is occurring one time, so I'm going to add this D in my final result. Then in this D only, because I'm just following this path, I'm going to add A, and this complete again I'm going to add this, okay. So this is how I'm going to do, okay. So these are the debug statements for example number 1, okay. Same way these are the debug statements for example number 3, okay. So you can just quickly go over these details, okay. You can pause the video and just go over this, okay. First try to write this debug statement by your own, okay, and then just compare them, okay. So this is the output for example number 3 debug statements, and same way this is for example number 2, okay. So here these are the paths. So just what first you are going to build the tree, then you are going to do the serialization, okay. Then here all these nodes you are going to get serialized like this, okay. Then you are going to check the frequencies. So y null is occurring 2 times, y null for this, okay, this here and this here. So you are going to delete this, all right. So you are going to again traverse from the top, okay. And while traversing you will find that some duplicates are there, so you are going to delete them, and in the end you are going to end with A, B and C, B, okay. So once we did this now, so now don't tell me that don't think that these are matching also, okay. For this, once you delete this, then you are going to say that no, here for this node B and that's it, okay. For this C, B have a B, okay. No, we don't need, we only need to do the deletion once only, okay. After that I'm just going to return, but I'm going to return A and B, A, B, C and CB, okay. So this is going to my output, that's it, okay. So now let's write the code, okay, and I'm going to explain all the lines of the code as well, okay, what I'm going to do, all right. So I hope that you guys are clear with the explanation part, all right. So now let's write the code, okay. So here, and if you want to practice more DSA problems, so you can also check my GitHub, okay. So here these are problems related to tries, okay. So you can find this, okay. So you can try to solve this 2185 440, okay. So in all these problems I have used tries, okay. Same way there are problems related to DB graphs, okay. You can check this, all right. Okay, so now let's write the code for this one. Let me just maximize the screen. So what we need, we are doing the serialization of the on the nodes, okay. So we have to create one class try, right. So here class try, okay, this is done. Now here I'm just going to create one string serial, all right. This is nothing but current node structures, okay. Current node structure serialized representation, okay. This is done. Then after that we have to create create the tree, right, try, right. So for that purpose I'm just going to create one map also, okay. So in one map string, okay, I'm just going to check this string, okay, from the root. This is my root, okay. After that, for this no root, I'm going to check if I have any key A, okay, this string A, okay. If yes, then I'm going to use that A, otherwise I'm going to create a new node A, okay. Same way if I want to insert this AB, so from this root I'm going to start. I'm going to check if I have this key A. Yes, from root I have this key A. Okay, A is nothing but string, right? Then after, once I reach A, then after that I'm going to add B. Okay, I'm going to check whether I have this key here. No, if not, add it. If yes, then just move to this one. Okay, right? So this is what I'm going to do. Okay, map string, and what I'm going to do, I'm going to use try here. Okay, so here children is equal to new hash map. All right, this is done. Okay, so this is nothing but current nodes, child nodes. Okay, current node, child nodes. Okay, current nodes, child nodes. This is done. Now here for try, we are always starting from the root. Okay, right? So here try root is equal to new try. Okay, this is done. Now after this we have to build a try tree. Okay, so what we have list of strings given to us like this, right? List of strings paths. Okay, so just iterate, just take one first, just take one by one. Okay, take this, okay, take this one by one. Okay, once we take this, then inside this also we have to check all the strings. Okay, so 2 for loops we have to use. Okay, 2 for each loops we can use. So here for list string path in paths. Okay, inside this my current. Okay, for all these, okay, all this always I'm going to start from root. Okay, so I'm just going to update my cur as root. All right, and now I have to iterate over all the strings inside this list also. Okay, so string, and these strings nothing but they are representing nodes. Okay, string node, I can say node path. All right, and now here inside this, for this root, okay, cur, here I'm just going to check children. Okay, cur and its children. Okay, so now here I'm just going to check if the current node I have or not. Okay, cur dot children dot put if absent. Okay, so if I have this node, then it's fine, otherwise just create this. Okay, if it is absent, then I'm just going to create new key node, and I'm just going to create one value as nothing but try node. Okay, so that is why I'm using try here. Okay, new try. Okay, I have created this try node. Right, now after that, once I create this, then I'm just going to move to the dat node. Okay, so I'm just going to update my cur as cur dot children dot get the value of this particular node. Okay, I'm just going to move to that node. Okay, so value means that node. Okay, so this is done, right? So this is how I'm going to build a try tree for this particular problem. Okay, build a try tree. Done. Okay, now once this is done, okay, so we have to also store the frequencies, right? So okay, frequencies of these strings that we are generating. All right, so for that purpose, here I'm just going to create one more hash map string, and here integer. Okay, frequency is equal to new hash map. Okay, this is done. Now hash table records the occurrence times of each serialized representation. Okay, post order traversal based on depth first search we are going to do, and we are going to calculate the serialized representation of each node structure, right? So here I'm just going to call this construct. Okay, construct, and in this I'm just going to root, pass the root and frequency. I have to store this. Okay, so I will take the help of this method. Okay, so this is done. Now in the end, what we need to return, we need to return this answer. Okay, answer is nothing but list of strings, right? And inside this answer we have different paths. Okay, these are the two things that we need. Okay, so here let's do one thing. Here let's just copy this. Okay, after this just paste it. Okay, list of string. Let's say this is nothing but my answer, final answer that we need. Okay, new array list. Okay, this is done. Now here one more thing, this is answer now, which is nothing but a list of strings. Inside this we have different paths also, which is nothing but a list of strings only, right? So here I can simply remove one list. Okay, So let's say I remove this. Okay, so list of string, and let's say this is nothing but a path. Okay, new array list, done. Now one we have to operate. Okay, once we calculate the serialization or everything, so we have to operate the trie. Okay, we have to delete the duplicate folders. So here first I'm going to construct, then I have to operate. Okay, so I'm going to call one more method, operate. In this operate, from root I'm going to start. Okay, and I'm going to do, I'm going to check the frequencies. Okay, and then what I'm going to do, I'm going to add the different paths, and I'm going to add this path to my answer. Okay, to this array list. So I'm going to operate this. So, and in the end, from here I'm just going to return answer. Okay, but what is the final answer value? Okay, so in operate only I'm going to operate this answer. Okay, and answer is going to operate using this path. And how I'm going to take path, I'm going to check the frequencies, right? So that this is done. Okay, so this is your base structure of this code. Okay, now only two things are pending. One is this construct, how we are going to do that, and what is the operate. Okay, so this is the basic of this, right? Okay, so now here let's write the construct. Very simple, nothing complex. Private void construct. Okay, and here inside this we are passing what, we are passing a node. Okay, try node, and after this we are just going to pass the frequency. Okay, so frequency I can simply copy this. Okay, this is the map of string integer frequency. All right, so now inside this, how I'm going to do the construct. Okay, so if it is a leaf node now, then there is no operational requirement, right? So here one base condition you are going to check, if current node, okay, if this node's children, okay, node dot children is empty. Okay, if it is empty, right? So if there is no such key, okay, for this node's children, okay, there is no key, so you can simply return from here. Okay, so you can simply write here, if it is a leaf node, okay, no operation is needed, no operation is needed, done. Okay, this is done. Now after this we have to create one array list. Okay, list of string. All right, and v is equal to new array list. Okay, this is done. So what is the use of this array list? Okay, so here these are the simple examples, right? But here if you see this example, for this a we have children coming from here and from here. Okay, so from here the children are going to come like this, c and d. Okay, so this is one list of string, let's say. Okay, then from here children are going to come like this, e. Okay, this is one more string. So now after this I'm going to apply the sorting on this. Okay, once I apply the sorting, then I'm going to iterate over all this, and in the string builder I'm going to append this. Okay, this is going to be one complete string. Okay, so that is why I'm going to use this, right? Okay, so this is done. All right, so here inside this just iterate over the all the entries in your map. Okay, all the children's one by one. Okay, so here basic. Okay, just remember it like this, map. Okay, then here dot e capital entry. Okay, map m capital entry e capital. Okay, and inside this, how we are going to iterate, we are going to iterate over this string and tries. Okay, so here just copy this, paste this, and here just give a common name. Okay, one by one we are going to iterate. Okay, here just say entry. All right, and here node. Okay, current node, initially it is root only. Okay, dot children. All right, dot entry set. Okay, so I'm going to check all the children one by one. All right, okay, this is done, right? So here inside this uh, I'm going to iterate over all the children one by one. Okay, so again I have to call the construct. Okay, so this construct, first we have to check the children's now. So here root a, then c, then d. Okay, once this is a leaf node, then I'm going to return here, and then I'm going to add this value. Okay, so this is what I'm going to do. Construct, again I'm going to call the children now. So here I'm just going to write entry dot get value. Okay, this is done. Okay, and here I'm just going to update the frequency. Okay, just going to pass the frequency every time. Okay, I'm going to call this method again. Okay, recursion. All right, so once I reach the leaf node, I'm going to simply return from there, and then after that in the v, okay, in this I'm just going to add the current value, okay, current side of children's value. Okay, so here entry dot get key. All right, I'm going to get that key, and here after this I'm going to use open and close parenthesis. Okay, this open, right, and after this I am just going to pass entry dot get value. Okay, so for the leaf it is going to be null only. Okay, value, right, and here dot serial. Okay, so serial simply means for this class trie we have the string. Okay, so that string we need to take a C, and C's value is this string. Okay, dot serial, so that is why I'm using this. Okay, get value dot serial plus, and here inside this close it. Okay, that's it. So this is the common pattern you need to follow. Okay, this is done. So once this is done, okay, once I get something like this, then I have to do the sorting on this. Then I have to use one string builder so that I combine the result. Okay, and once I combine the result for this node A, I have to add this serialization complete. Okay, so this is my next step. All right, so here collections dot sort v. Okay, this is done. Then after that create one string builder, string builder sb is equal to new string builder. Okay, and then after this just iterate. Okay, so all the strings we have, okay, string s in this v. Okay, all the strings we have, iterate over them and then just append them. Okay, sb dot append s. Okay, done. Now the current node, okay, current node where we have, right, so node dot serial, I'm going to update this for this node, the serial as sv dot to string. Okay, I'm just going to change it to string, and now side by side just update the frequency. Okay, how many times this appears. So frequency, okay, your map, okay, frequency dot put, what is going to be your key is going to be this node dot serial. Okay, this string, okay, node dot serial, this is going to be your key, and just check if in this map this key is already there or not. Okay, so get or default. Okay, if it is there, then take the existing value of this. Okay, node dot serial existing value. If it is not there, then take 0, and in that value just add 1. That's the simple meaning of this line. Okay, this is done. All right, so this is your construct method. That's it. Now final, that is nothing but operate, and it is also very simple, nothing complex. Okay, so here private, and after this void and operate, and inside this what you're going to pass, we are going to pass try node. Then what you are passing, then you are passing frequency. Okay, you can just copy this, then you are going to pass path and answer. Okay, this, and then you are going to update path. Okay, so you are just going to pass this, and then you are going to update this answer also here. Okay, this is done. All right, so here in this map string integer frequency, list string path, and list of string answer, these are the 4 things that you're going to pass. Okay, so here if inside this, if frequency dot get or default. Okay, get or default. Okay, so I'm going to check the frequency of what, of this serial key. Okay, node dot serial. Okay, so if this key is there, okay, then take that value, otherwise just take 0. Okay, if it is greater than 1, then that means if the serialization representation appears more than once, it needs to be deleted. Okay, so here I'm just going to simply return from here. Okay, return. So what I'm saying, if serialization appears more than once, okay, then it needs to be deleted. You can say it needs to be deleted. All right, okay, this is done. Okay, so now once this is done, then after that I'm just going to check if my path is not empty. Okay, so if my path is not empty, right, so in that case I'm just going, in the answer I'm going to add the result. Okay, so in the answer you are only adding the paths, okay, which are non-empty, right? So you are not adding the root, okay, so that's why I'm writing this. Okay, new array list, okay, and here inside this you are going to just add the path. Okay, so initially it is empty in the starting, okay, right? So that's why I'm not going to add anything in the answer, okay, the final answer that you need, right? So now first we have to update the paths. Then once we get some path to that node, I'm going to add it to answer. Okay, then I'm going to again modify that path, okay, if there are more children after that. And once I execute all the children, then I will just backtrack, okay, empty, I will empty all the paths. Okay, then again I'm going to check the another branch. Okay, so this is what my plan is. Okay, so here for again I'm going to use this, okay, map.entry. You can just copy this. Let's see if we can copy this or not. Okay, let's see. So here for map.entry string try entry, and here node.children entry, I think it will work. Okay, so here inside this we can simply in the path I'm going to add. Okay, so here path dot add, and here entry dot get key. Okay, this is what we need to add in the path. Okay, entry dot get key. Okay, so once this is done, okay, now here again I'm going to call the operate. Okay, and this time in the operate, okay, I'm going to first node I'm passing now. So here in the node I'm just going to pass entry dot get value. Okay, value. All right, and then after this I'm just going to update same frequency, just pass frequency path. Okay, and answer. Done. Now this is how we need to operate. Okay, and in the end if I'm going to start the new branch, so I have to remove this also, right? So here path dot remove. Okay, path dot remove, and what you are going to remove from this path, you can say path dot size. Okay, you can say path dot size. Okay, for backtrack. Okay, so -1. Okay, last value just remove. Okay, one by one, right? This is done. All right, so that's it. Okay, now let's run the code and see if the code issues. We'll try to fix that. So all the test cases has been accepted, right? So now let's submit it. So see, our solution is set, right? So here what is happening, I'm checking the children's, right? First a I'm going to add, then again I'm going to operate this. So right now path is not empty, so I'm going to add a, let's say. Okay, then again I'm iterating. Okay, a child, I get b. Okay, again I'm going to call this. So in the path only I have a add a b. Okay, so in the answer first time I have added a, now I have added a and b both. Okay, now after that there are no children, I'm going to remove the last one. Okay, then again I go backtrack, there is no children, I'm going to remove it. Okay, now I'm following the new branch. Okay, so this is what we need to do. Okay, so if you want to check the time complexity for this one, so I think I have added the time complexity details somewhere here. Let's see. Yeah, so here first what we are doing, we are building the tree. Okay, so we are using this for loop, then this for loop. Okay, so here each path has at most L strings, so we insert n such paths. So you can say n into L for the build the tree. Okay, there are some code here. Okay, but we are mainly doing these things. Okay, build the tree. Then we are construct the serialized representations. Okay, construct root frequency. So in construct we do a post order DFS. For every node we serialize all its children, sorting the child serialization and concatenating them to string. Okay, so traversal cost, each node is listed once off, and serialization cost, each node children on average k are sorted and string concatenated. Okay, so sorting is of k log k. Okay, concatenating up to L for strings of total length. So you can say of n into k log k total length of all serialized string. Okay, so you can simply say n into log n. Okay, same way we are operating the DFS for the final answer. So here also n into L. So overall time complexity you can say of n into log n plus n into L. Okay, so n is nothing but total number of try nodes, L is nothing but max depth of any path, and k is the average branching factor. All right, so n into L goes to build the try, n into log n goes to serialize and count frequencies, and n into L goes to get the result. Okay, so I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.